Dear friends, hearty welcome to the online problem solving session series organized by Maths Aspirants groups. Today we have a session focusing on ISI MMath entrance exams on the subject linear algebra. We have Mr. Abhirup Das, a research fellow, TCG CREST, Kolkata, as the resource person for today's session. I would like to thank Mr. Abhirup for inviting our invitation and joining with us. I hope that today's session will be really helpful to all those who are seriously preparing for ISA exams. I welcome everyone to this program. Welcome, Abhirup.
So the way our sessions go is a little bit different from, a normal problem solving sessions. We don't just pick up discrete problems and solve them. Those are also very important sessions, I would say, because you need those skills. You need that particular skill to, clear the exams. But what we try to do is a thematic session. Like, suppose there is a central problem, okay, for every session. And we sort of try to reach that problem via a path, and that in that path we will see some types of road breakers. Okay, some types of road breakers are there. So that's why we try to organize this session. So okay, so let's start. Okay, let's pose a question first and then see how can we do things first. Okay, so this is our central problem. Okay, okay, so you can see the matrix looks like this. So like the first entry is 1, then this one is 1 by, so this is the 1/2th entry, right? 1 plus 2 minus 1, that is 1 by 2, 1 by 3. And similarly, you can see that it is a symmetric matrix, so on. Okay. So we are asked that whether what is the rank of this matrix, whether is the positive definite or not. So first, let me tell you, if you don't know the definition of a positive definite matrix. So A belongs to, so first let's take a field, let's take the field MNC, or maybe, yeah, let's take the field MNR. Okay, so A belongs to MNR. Is said to be positive definite A belongs to MNR is said to be positive definite if for any x belongs to R to the power n. Okay, x transpose AX is strictly greater than 0. Okay, that is, x transpose AX is always strictly greater than 0 whenever x is non-zero. Okay, so these type of matrices are called positive definite matrix. So an immediate example is that the identity matrix. Okay, so you just take x transpose IX, which is x transpose, say suppose write x like this. So you will see that this is right. Okay, so if x is non-zero, summation xi square is also non-zero. So this is the definition of a positive definite matrix. Okay, one example definition. But see, you have been given this problem. Do you have any idea how to approach it? Because see, this problem was once given in NET. Okay.
So tell the definition again.
Yes, it is written there, right there. A belongs to MNR is said to be positive definite if for any non-zero x, x transpose AX is always greater than 0. See, x transpose AX will be what? X transpose AX is a positive
A
number.
1 cross 1 matrix. This will
No. X transpose AX is a scalar. Just
but this is a matrix, so this will be reduced to 1 cross 1 matrix.
yeah, 1 cross 1 matrix.
Which
So
is a
basically, which is a scalar. Okay. So that is the definition. So this problem was came in net. Okay. I have seen people approaching this problem in a completely wrong way. Okay. First of all, they say that you write down a few matrices, you check the rank, you check it. I mean, that is not at all the way to look at it. Okay. So I will, once I conclude the session, once at the very end of the session, I will tell you what is the problem with this approach. I mean, with the other approaches, and why people are so prone to making those mistakes. Okay. So let's start. So first, tell me. First, we go to problem 0 and see, which is apparently a very non-correlated problem with this, with the question that we have posed right now. Okay. This is question 0. Can we define an angle on any inner product space? So suppose V is a vector space over F. Okay. Can we define an inner product over V? Because you see, no other information is given. Okay. Only one thing is given, that is this thing. Okay, but V is over if this F is actually R or C, because while defining inner product, we could take either R or C. But that can be any, I mean, infinite dimensional vector spaces. I mean, everything can be there. Oh. Can we define an angle? So by that, what I mean, suppose you take V and W belongs to capital V. Okay. Can you define an angle between V and W? Because you see, this might be infinite dimensional vector spaces. So no longer you have those pictorial diagrams. Okay. The answer is yes. So think about it. Okay. So think about it. This is discussion. Think about R to the power n. Okay. Take V equals to R to the power n. Do you remember what is the inner product? That is the dot product, right? So if V is V1 to Vn, and if W is W1 to Wn, do you remember what is V dot W? I mean, that is the inner product is basically the dot product, right? That is summation Vi Wi, right? Right? But we also know that this is nothing but the dot product between V and W. I mean, I should say V transpose and W, right? Or maybe V dot W is good enough. So when we talk about this dot product, what is the formula? The formula is norm V times norm W times cos theta, right? Where theta is the angle between V and W, right? Theta is the angle between V and W, right? So you see, so you already have this, right? So let's just put it this way. That is your equation, right? So you see, you can define cos theta by this. Okay. That is V comma W is times norm V comma V, norm W comma W. Okay. So that is the formula for cos theta. We will do the same thing here. Okay. So an inner product is given on V. Okay. So for any V and W, you just define that way. I mean, so V and W belongs to that V. You define theta to be cos inverse inner product v comma w, because the inner products are defined on that set, root over v comma v, root over w comma w. Okay. So in this way, you can define theta, I mean the angle between any two vectors in any given inner product space. Okay. Okay. V and W is vector spaces. It is single non-singular transformation. If W, then show that. Is anyone asking a question? Somebody, I think, raised a hand. Yes. You raised a hand. I mean, why is that? So you see that. So you know the definition of an inner product, right? So what we will try is that to solve this problem. Okay. So
Sir,
yeah.
In previous, for defining theta,
Hmm.
if v is zero vector, then how will you define theta? What is the theta?
If one of the vectors is 0,
Huh?
sorry.
Yes, sir. One
I
of the
mean,
vector is
no. You can only define an angle between two non-zero vectors, right? I mean, even in Rn, can you define? I mean, suppose in R2, okay. So this is one vector, okay. This is V, and suppose your W is 0. That is the origin. How can you define a I mean, 0 vector is a point, okay. So you understand that? So it's not possible to define an angle between one line and one angle.
okay, sir. But okay.
Yes.
But this 0 point.
Sir, what is the conclusion of question 1?
What is the question? The conclusion of question 1. Wait a minute. Did I skip the question 1? Oh, sorry. Extremely sorry, dear. We should have gone to question 1. I mean, this question you are talking about, right?
No, sir. Actually, I was talking about the question
Zero,
of
right?
angle question.
Okay. No, the conclusion is that yes, we can. You see that we have just defined it. We just defined it. You see?
Means we can define angle between any two vectors,
Yeah.
two non-zero vectors.
Any two non-zero vectors, you can define an angle, and you see
Always.
V is, yeah, but V has to have an inner product, else you can't do it. Because you see in that expression, while defining theta, we took the help of the inner products. You see,
Yes.
the only thing you need is that an inner product defined on V. That's it.
Okay, Dada.
Okay.
This is a class CSR net.
No, not at all. Mathematics is not segregated by examinations. Okay. I have taken a net level examination, a net level question, which I thought was very, very good. So That's how I designed the session. It's not
But
like
sir,
that.
I am preparation for IIT exam and my medium in Hindi.
Mm, okay, that's a bit difficult for me. I mean, I'm comfortable in English and Bengali. Hindi I can speak, but in writing, and I can't go on for 1.5 hours explaining things in Hindi actually. This is a,
And
I think in the session, in the advertisement, we mentioned that there will be an MMath level problem solving. Okay, so the questions I am picking, these are all MMath level questions. It is not, it is not meant to be taken from the previous years of ISI actually. I mean, we can do that as well. But if an MMath level question is there in the TIFR paper or there in the NET paper, I mean, why shouldn't we take it?
Hello sir.
Yeah, go ahead.
Actually, I am complete IIT exam real analysis. So which class starting real analysis like question?
See, the thing is that we have designed this, organized this session for MMath because IIT exam is already gone, okay? And MMath is just on the horizon, on 11th May. So उसके लिए हमने ये बनाया है, ठीक है? So IIT exam के लिए और या नेट के लिए वो फिर बाद में होगा.
Okay guys, carry on. No disturb.
So so if n plus 1 the space of column matrices over n, okay? So basically f to the power n. Q is an n cross n invertible matrix over f, okay? They are asking that show that this is an inner product on f to the power n plus 1, okay? So you know what is Q star? Q star is the conjugate transpose of Q, okay? Q star is the conjugate transpose of Q. Okay, for simplicity, let's just take R throughout the field, okay? So then don't
What
think
is
about
conjugate in general F?
Sorry?
What is conjugate in a general field F?
What is conjugate in a general field? No, actually, when we're talking about inner products, the F is assumed to be R or C, okay? Else you can't talk about conjugates, okay?
Okay, thank you.
We can define it in a way. When we write about A plus IB and A minus IB to be conjugates, we use this I, right? This I is a root of the equation x square plus 1, right? So for any F, you can define the conjugate of to be A plus, say you write this A plus alpha B or A minus alpha B. These are conjugates and alpha is a root of x square plus 1, okay? So in a general conjugate, we can define that way. But while talking about inner product, F is taken to be R or C, okay? So, okay, for the time being, just take transposes because we haven't defined the notion of conjugate transpose and all that. It's nothing. Just Q star is just Q transpose whole bar. Okay, you transpose Q and you take the conjugate of every element. That's it. But okay, let's take transpose for the time being because we are doing things on R. Okay, so we have to show that this is indeed an inner product. Okay, let's see. So first of all, you see that what is X inner product X? That is X transpose Q transpose Q of X, right? And you see what is that? That is QX whole transpose QX, right? Right? So this is nothing but Y transpose Y, where Y equals to QX. And we all know that Y transpose Y is what? Summation yi square, right? So it is always greater than equal to 0. But then we'll have to show that if it is 0, then X has to be 0, right? So the first condition is satisfied that it is indeed greater than equals to 0. So if X transpose X is 0, then we mean that summation yi square is 0, by which we mean that yi square is 0. In particular, yi is 0 for all I. for all I, right? By that we mean Qx is 0, and by that we mean x belongs to kernel. I mean, you can directly write x equals to 0 because you see q was invertible. Okay. And the linearity you can check. I think that lambda x plus mu x prime plus y. I mean inner product y. You can check this. This will hold. Okay. Just take. So what will it be? Lambda x plus mu x prime transpose q transpose qx. Okay. It will just be additively distributed. Okay. And you will get just lambda times x inner product y plus mu times x prime inner product y. These are just basic computations. So this is indeed an inner product. And here they are asking, take an appropriate q and derive the standard inner product on this. Okay. So this is just obvious, right? Take identity. Take q equals to identity, right? Because then your x transpose, it is identity transpose x, right? That is summation xi square. Or maybe you can just take y. Okay. So you will be getting summation xi yi. Okay. Where x is this and y is this. So that's enough. So you can take q equals to identity. Okay. So that is problem 1 gone. Now you see the same thing we have done with invertible matrices. We will be trying to do the same thing, exact same thing with linear transformation, non-singular linear transformations as well. Okay.
Sir, can you show the solution of the last question?
Yes, just
Of
give
the
me.
recent question, please, once.
Are you copying it? I will send the notes, so don't worry.
Okay, sir. Okay.
Okay.
Actually, I was copying.
No. Yeah, I doubted it. So I will be sending the notes. And the
Okay.
video is being recorded. Okay. The recording link will be sent.
Achha, okay, sir. Thank you, sir.
It will be actually the video will be uploaded to my channel, the channel of my academy. So I will be sending you the link, and it will be an open video. I will request you to send the link to everyone. Okay, so that everyone can see.
Okay, Dada.
What should I say? Yeah. So T is a linear transformation from V to W. Okay. What is your name, by the way? Because I can't see the screen while I'm writing. Okay, fine. So you see, the problem is that W has an inner product. Okay, so there is an inner product in W. Okay, so suppose this is an inner product in W. Let's write W in the subscript. Okay, this is defined on W. With the help of this linear transformation, which is non-singular, we want to define an inner product on V. Okay. So we will take the trick, we will inherit the trick from the last problem. No? So what we do is that you take alpha and beta belongs to V. You define that inner product alpha, beta, V, which they have given this notation by Pt alpha beta. They are defining it to be T alpha inner product T beta. Okay. In W. So you see alpha and beta was in V, right? T alpha and T beta are in W, where there is already an inner product defined. So you are taking the help of that inner product to define the inner product in the domain, right? So now let's see whether this is indeed an inner product or not. So you take alpha, inner product alpha, right? it will be what? This thing, T alpha inner product T alpha, right? Now see, this is always greater than equals to 0, right? If alpha inner product alpha V is 0, then what will you have? This term will be 0. T alpha inner product T alpha will be 0. But then you have T alpha equals to 0 because from the property of an inner product. But then you have alpha equals to 0, right? Because T was taken to be non-singular. The additivity and all those parts are pretty easy to check. Okay, so you can just take alpha 1, alpha 2, and beta, and you can think about alpha 1 plus alpha 2 plus beta V. So you will be getting T alpha 1 plus alpha 2 plus T beta W, that is T alpha 1 plus T alpha 2 plus T beta W. So distributed additively, T alpha 1 inner product T beta 2 plus T alpha 2 inner product T beta. So that is alpha. This is the notation of definition. Okay, that's why I changed the notation. Okay. The scalar part will also come out. You can check it. Okay, you should not be repeat. So you see, we had an inner product in the codomain. We sort of inherited it. We sort of pulled it back to the domain. Okay. Now, for the application, for the direct application of this, let's do this. Okay. Part B. So while they are taking it complex valued, okay, just take it real valued, okay, because we are doing everything on R. Okay. So this inner product will not have this. Okay. So if inner product G will be defined just by 0 to 1. Actually, when I made this problem set, I was thinking about doing it in more generality. But I think for math level, let's not go into the conjugacy because general conjugates and those things, those are not needed yet. So this is an inner product. We will show that this is an inner product. Okay. The vector space taken here is, so V is C01. Okay. That is set of all continuous functions from 0, 1 to R. If from 0, 1 to R continuous. Okay. So tell me, what should be my approach? So basically, you can see that we will have to define an appropriate linear transformation which is non-singular, right? And then we are done. So can you tell me what is that? Can you tell me what is that? Observe another thing. While doing the problem V, while doing the problem 2A, we did not talk about the dimension of W or V. Okay. V can have bigger dimension, W can have bigger dimension. We did not need any restriction or constraints over W to sort of to solve the previous problem. Okay, so one way to check is just by hand. Okay. You can check it by hand. That is, you take if belongs to C01, right? And take if belongs to C01. So integration 0 to 1, what will be the inner product of f comma f? What will that? It will be ft square dt, right? So you see the term inside is always positive, right? The integrand. So it is always greater than equals to 0. But what happens when f comma f is 0? Can you tell me? So does it imply f equals to 0? Does it imply? Hello? Does it imply f equals to 0?
Yes.
How do we prove it?
It is not zero, take a point where it is not zero, and in an interval it will be positive.
Very good. Very good. So he is saying that claim if gt is greater than equals to 0 for all t belongs to 0, 1, then integration gt dt (0 to 1) implies gt is 0 for all t belongs to, right? So he is saying that if we integrate a positive function and get 0, it means the function is 0. But it will require some proof, I mean the one he was alluding to. So suppose not, okay. Let me first draw the picture. I think it will be easier for you to understand. So see, if g is non-zero, there will be some, I mean a point where it is just non-zero. If it is not identically 0, there will be a point, say x0, where it is non-zero. Maybe we can write it t0. So since g is always non-negative, t0 is positive. So he is saying that there will be an interval in which gt is positive because of the continuity. So there you have the integration. I mean this area, this is non-zero. So the integration will never be 0. Suppose not. So we will just write it down, okay. Then there exists t0 belongs to 0, 1 such that g of t0 is non-zero, right? Since g is greater than equals to 0, gt0 is strictly greater than 0. Okay, non-zero, it could be negative or positive. G0 is strictly greater than 0. Now, so for continuity, you take, so since g is continuous at t0, for every epsilon greater than 0, there exists a delta such that if t belongs to t0 minus delta comma t0 plus delta, gt belongs to g0 minus epsilon comma g0 plus epsilon, right? So take epsilon strictly less than gt0, okay. So then it becomes positive, right? So if epsilon is, so this implies 0 is strictly less than GT naught. GT naught minus epsilon, right? Right? For this epsilon, we have a delta such that if T belongs to T naught minus delta comma T naught plus delta, then what was happening? GT was lying in between this, right? GT naught minus epsilon comma GT naught plus epsilon, right? But we have seen that this is greater than 0, right? This was greater than 0, right? So GT is always positive when T is in this neighborhood, okay? So here you can see this is plus delta, I mean this is T naught, and this is our plus delta, and this is our minus delta, okay? So this is the neighborhood, okay? No, let's that should do it. That should. So you see, when you are integrating 0 to 1 dt dt, it is clearly greater than 0 to 1 integration. I mean, this is clearly greater than T naught minus delta to T naught plus delta gt dt, right? And as you can see there is an area. So this is strictly greater than 0. Okay. So if G has a, so G is not identically 0, the integration of G won't be 0, right? Given G is positive. So there you can put ft square equals to G to get that f square will be 0. So you will be getting, putting G here, you will be getting f square t equals to 0. That will imply ft equals to 0. Okay. For all t belongs to 0. The linearity part will be easy to check. Okay. You can just check it. You can just put f1 plus f2. The integration is additive. So we have established it. Okay. That this is an inner product. Let's move on to problem 3.
Sir,
Yeah.
in 2A, what is the need of non-singular linear transformation?
Just a moment. Just give me a minute. So you see for this step.
2A.
Yeah,
No, sir.
this is 2A. So
2A.
QX, yeah, I'm doing 2A.
Question number
Oh,
2A.
Sorry.
Yes, sir. What is the need of T is non-singular?
There it is.
Okay.
E alpha 0 implies alpha equals to 0. That's the property of non-singular linear transform.
Okay. Sir. Okay.
Because you see, I mean, you will have to get it right. I mean, two non-zero vectors, if you do the inner product, they cannot produce a 0, cannot produce 0, right? To ensure that you need to be non-singular.
And what is the need of into mapping?
Sorry?
Into mapping. T is V2W into mapping.
No. Don't go into that. I mean, into, onto, these are not, I mean, these are, you think into means one to one, right? Injective. No, don't. I mean, Hoffman doesn't use that terminology.
Okay, sir.
Into, I mean, don't. Okay, so T is a linear map from V into W means V to W. Just that. I mean, into doesn't have any extra meaning here.
Okay, sir. Thank you.
So what happened to the B part? Did we do the B part?
Yeah,
Did
we
we
were.
make an example, new example?
Sorry. To be. Yeah, we were doing that.
Yeah.
To be. This was the solution of B. I mean, have you missed
You
it?
proved that this integral FG is an inner product, right?
Yeah.
Okay, I thought that I saw a problem which says we take V equal to W and to make a new inner product.
No, okay. So, I mean, we did not use that approach actually. We have proved 2A and B separately. Okay. Oh, so you are thinking, I mean, the first hint I gave you that let's define T first, right? Then we can go to that, right? No, I didn't do that. I just proved it directly because I think it will be easier
Okay,
to prove it directly. The direct taking is easier.
okay, so you this inner product and that's it. You didn't make a new inner product.
Yeah.
Okay.
Okay, so this says that let A be a 2 cross 2 real entries. X, Y belongs to R to the power 2 R square. For X, Y belongs to R square. Let F A X, Y is Y transpose AX. So that F A is an inner product. Okay, first let me tell you about. So you understand what do they mean by saying F A is an inner product? So they are defining this X inner product Y to be this. And they are telling you to check that if it is an inner product, then this will happen. They are telling you to check that if this is indeed an inner product, this will happen. So let's do one thing. First, define an inner product matrix. So suppose this is an inner product defined on V. Okay. So inner product has certain properties that over reals, you know that VW will be equal to this, right? Inner product is symmetric over reals. Over complex, we need a conjugate. So what is an inner product matrix? So take a basis beta equals to say alpha 1 to alpha n of V. We say that the matrix of this with respect to beta is, so you denote this by that. It is nothing but the matrix you understand the matrix. That is the ijth entry of the matrix is basically the inner product of alpha I and alpha j. Clear? Is that clear? Is the definition clear? That what is the matrix of an inner product with respect to a given basis? Is the definition clear?
Yes.
In your question, you have written A11 positive, A22 positive, determinant positive, right?
Mhm.
If we have A11 positive and determinant positive, A22 automatically becomes positive. So that
Hmm? Why?
I mean, if A11 and determinant is positive,
Huh?
A22 is automatically positive, right? If you have A equals A transpose, it will be like A, B, B, C. If A is positive and AC minus B square is positive, you need C to be positive. So that's a redundant condition.
Sorry, that is A, B, B, C, right? So you are saying that if AC minus B square is greater than 0, then C has to be greater than 0. I mean, that is your
And
argument.
A is also greater than 0, then C has to be greater than.
Yes, I mean, this has to be, this has to be a positive quantity bigger than this. No, I mean, so you see, I mean, what is the problem is that it is needed for the if and only if condition. Okay.
Yeah, it still stays, right? Irrespective of that, if beta is positive, then A22 is automatically positive. So, okay, yeah, you continue. Thank you.
No, I understand that actually, but you know what? There is a reason they have mentioned it. Okay. I mean, there is a reason they have mentioned it in Hoffman points. I mean, we will show that this is true for any n cross n matrix. That every diagonal element will be 0. That's the thing they want to point out here. Okay. So that's the reason they have, added this redundant condition so that you can notice it actually. Otherwise, you are right. For this particular 2x2 problem, no, it is not needed. So this is your inner product matrix, okay? And you see that. So suppose you take x equals to summation xi alpha I, okay, and y equals to summation yi alpha I. What will be your x inner product y? What will be your x inner product y? So it will be, if I'm not mistaken, it should be summation xi alpha I, inner product summation yi alpha I, right? Upon calculating the inner product, you will get an I j xi yj alpha I alpha j, right? Right, that is. So let's call it A. Isn't it equal to this? Isn't it equal to this? Do you understand it? What is this thing? What is xi yj? What is xi yj times bij? It is nothing but x transpose by, right? Where B is this matrix. That's what we have written. So you see, immediately you get the inner product is basically expressed in terms of this. Right? So the point of defining an inner product matrix is that so that you can write it x transpose something y. Okay, that's the whole point of defining an inner product matrix. Okay, so clearly this inner product matrix will have certain properties. What are that? So one, you see that x inner product y, so you will see that x, if x is non-zero, then x inner product y, x inner product x is strictly greater than 0, right? Which implies putting y equals to x here, x transpose ax is always greater than 0, which means A is positive definite, right? It means A is positive definite. That is the first time we have mentioned positive definite after the first given definition. So there we are trying to bridge a connection between positive definite matrix and inner product. Okay. So it's positive definite. That is one thing. Another thing you can notice is that so if you put x equals to 1 0 0 0 0, okay. You were saying something regarding 3, right? You see, what I'm trying to say is that if call it E1, huh? And that why do we need A22 to be greater than 0? And I told you that for 2 cross 2 we don't need it, but for greater you will need it. So what is x transpose AX in this case? Anyone? That will be 1 0 0. Sorry, it will be the first. It will be the 1 1 entry of A, right? So you see, for this you will be getting what? Alpha 1 inner product alpha 1, right? The first entry of A, okay, which is greater than 0, right? So the inner product matrix is positive definite, okay. The inner product matrix is positive definite. Is this of full rank? Is this of full rank?
Yes, sir.
Yes, right? Because let X belongs to kernel A. So then AX is 0. It means X transpose AX is 0. But it is what? It is X inner product X. So it means that X is 0. Okay. So you have A to be a full rank. Look at our problem. Okay. We will prove it in more generality. Now the opposite. So given a positive definite matrix, follow-up question. Given a positive definite matrix A, can we define an inner product? This is in M and R, okay. Find an inner product on R to the power n such that the inner product matrix with respect to the standard basis is A. Can we do that? So they are saying that take beta equals to E1 to En. You know that elementary vectors. They are saying that define an inner product in a way so that this matrix becomes A. And I say the answer is yes. So you just define it this way. You define X inner product Y to be X transpose AY. That's it. But then we will have to check that whether this is at all inner product or not, right? See, the additivity part will be taken care of. That's why I'm not going into that. The linearity in first coordinate, linearity in second coordinate, scalar multiplication. These are easy to check. So I'm only bothered about this non-zero part. So if you take X not equal to 0, what is your X inner product X? That is X transpose AX, right? But this is strictly greater than 0 because A is positive definite, right? So it is indeed an inner product. It is indeed an inner product. Okay. Now let's see what will be the basis. I mean, because then you will have to show that the basis, the inner product matrix with respect to the elementary basis of the standard basis will be A. So what was this? If you remember, what was this? What was the ijth entry of A? It was EI, inner product EJ, right? Right? No, I have used two different notation. Just a minute. Should have stick to one notation. Just a minute. So it will be X. Sorry. Right? So the ijth entry of A will be this, right? So EI, right? Don't think that this will be 0 or 1 because we are not taking the standard inner product anymore. We are taking the inner product defined on this. Okay? We are taking the inner product defined on this, right? So from our definition, what will this be? This is EI, EI transpose A, EJ. What is that? That is AIJ, right? Right? The ith column and the jth column, inner product of that, right? EI transpose A, EJ is AIJ, right? So that is indeed the entry of AJ, right? So it is proven, right? Hence, when you compute this inner product with respect to this, you get back the matrix A. Because how was the inner product matrix defined? We took a basis, we took the inner product with the ith vector, the jth vector, and we put it in the ijth position of A. You see? So it is matching there that with respect to this basis, this inner product is basically will yield this, right? So is that clear now? That why A is the inner product matrix with respect to beta for this particular inner product? Is that clear now? Hello, is it clear? Or should I repeat it? Hello.
Sir, clear, sir.
Okay, thank you. So we have an inner product matrix, a inner product induced from this. But you take a corollary of that. Take a corollary. Take I equals to J. What do you get? What do you get? You get EI, inner product EI to be what? AII, right? But you see, it has to be greater than 0. So you observe that every diagonal element is greater than 0. Every diagonal element is greater than 0. Okay. And also you observe one more thing. This was corollary 1. Corollary 2 is EI inner product EJ, it has to be EJ inner product EI because the inner product is defined over R. Over R inner product is symmetric.
Yes, sir.
So you get AIJ equals to AJI. That is A is symmetric, right?
Yes, sir.
So you know that a symmetric matrix, so corollary 3, determinant A is strictly greater than 0. So from 2, you know that A is symmetric. So you know that A has, since A is symmetric, A has all real eigenvalues, right?
Yes, sir.
Since A is of full rank, these real eigenvalues all have to be non-zero, hence positive, right? A has all real eigenvalues. Since A is non-singular, every eigenvalue of A is non-zero, right? I mean, a non-zero, is that clear? A non-singular matrix cannot have zero as an eigenvalue. So say lambda1 to lambda n are eigenvalues of A. Suppose A vi is lambda I vi. Okay, that is lambda I. I mean, that is vi is the corresponding eigenvector. Okay, that is vi is the corresponding eigenvector. Now you see, what is vi inner product vi? What is that? That is vi transpose A vi, right? That is vi transpose lambda vi. That is lambda vi transpose vi, right? You see, this is strictly greater than 0 because vi is non-zero, right? Eigenvector is non-zero by definition. This is strictly greater than 0, right? No, sorry. Vi transpose vi is just there, right? What is that? Summation lambda vi square, right? This quantity inside the bracket is non-zero, right? Because v is non-zero. Vi is non-zero by definition, right? So we have lambda summation vi square I running from 1 to n to be strictly greater than 0. This means lambda is strictly greater than 0. Okay? Sorry, lambda I. Okay. So you see, any eigenvalue of a symmetric matrix, I mean of a positive definite matrix is positive. So the path was from the positive definite matrix, we have defined an inner product. And from the inner product, we see that the matrix is symmetric. So since it is symmetric, is that all the eigenvalues to be real? Since A is a full rank, A cannot, no eigenvalue can be 0. And then again from the property of an inner product, we have induced that each eigenvalue of a positive definite matrix is positive. Okay. Now to prove corollary 3, you see what will be determinant A? This will be product of the eigenvalues, right? That is positive because each of them is positive. Clear? I mean, who was asking the question? I mean, the one I was talking to regarding this problem.
Yes.
Yeah, you understand that. I mean, why what is needed to see the trace and all that?
It's not needed, but it's a corollary. I can see that it's a
Yeah,
corollary,
it's
but
a
it's not.
corollary.
Yeah.
I mean, but the other thing is that suppose you have been given A equals to A transpose and every thing is real there and determinant A is greater than 0. So can we induce from there an inner product? I mean, can we induce from there that A is positive definite?
Yeah, if eigenvalues are real, then positive.
Yeah, but I mean, these are not eigenvalues, right? These are only the diagonal entries. But,
But
then you will have to,
boundary
take
condition, you have
an
the
orthonormal basis. Yeah. You will have to diagonalize it, right? Yeah. So that will be.
A equals A transpose, it's diagonalizable. So
Yeah. Okay. So let's move on to this problem now. Now let's move back to our. We are almost, at the end of the class, end of the session. This was our problem. Okay. I'm giving you 1 minute to just look at it carefully. I will give you 1 minute. See this problem. Give me 1 minute. Just take some water.
Sir, if we write the matrix A, this is the form of 1/2, 1/3, ... 1 by n. And next row started with 1 by half something. Hello?
Sir, here there is a question. The A isn't given that it is like what is it n cross n matrix or something else? That is not given here.
Yeah, we are assuming that it's an cross and matrix.
Hello. Actually, I had to go to the filter. Aquavit to fill it up. That's why it took more than 1 minute. Yeah. Are you asking anything?
No, I was just saying that it was not given that it was n cross n matrix or something. So it can be done inductively. Like for n equal to 2, the rank will be 3, and for n equal to 3, the rank will go and so on, and we can inductively show that.
So how can you show it inductively? How can you show that? Okay, so and say suppose I have this matrix. So suppose I have this matrix, okay, 1 by 2 up to 1 by n, 1 by n, and all these matrix, okay. And there I am adding an extra column for your induction step, right? So it will be 1 by what will it be? It will, I think, be 2n plus 1, right? Yeah, that will be.
Yes.
Yeah. So how will you say that this matrix from in the induction step? What is your from? So assuming it to be true for n, how will you move to a rank higher?
If we look at let's say if we look at the principal diagonal, a11 will have 1, a22 will have 1 by 3, and so on. So the next term, in n plus 1th term, diagonal term will be 1 by 2n plus 1, and for the same row, I mean,
Mhm.
for n plus 1th row, it will be 1 by n plus 1. And as I'm actually checking here that there's a symmetry for like A
Yeah,
of
yeah, yeah. There is of course this is a symmetric matrix. Then
A
what?
of yeah, and A of Ji will have the similar values. So by that sense, I've said
No, no. I'm still trying to get to the argument for rank. So what is the argument for the rank? I mean, how will you show that if we put a symmetric column here and here, the rank will be increased just by 1?
sir, I have only checked it for one. I mean, it was
Yeah,
my basic
that's the
exam.
problem. That's the problem. Your intuition is correct, but how will you write it down? Your intuition is absolutely correct, but how will you write it down? No, by any means, do you guys think that when you are given this problem in the net, you will have to go through these 4 pages? I mean, is that what you think? No, not at all. I mean, when you are suppose you have been given a problem. Okay, so we are trying to develop a story around the problem. You understand that? I mean, okay, let me solve it first. Okay, then I will tell you, and you will recognize. I mean, this is the one-click problem, just a one-click problem. Okay, it will not. It shouldn't take you more than 30 seconds to solve it. So you see, we have just shown that V was our C01. Then we defined an inner product between F and G to be FT right? DT. It was an inner product, right? Now you see,
Yes, sir.
I mean, yeah, you assume Rx as a subset of C01. Okay, that is, we are taking the polynomial function. So you understand what I mean? You are only, so by that I mean, when you are taking Px belongs to Rx, we are considering Px to be a function from 0, 1 to R, right? It is of course continuous because it is polynomial, right? So you see, so you take any two polynomials from Rx, okay? Take fx, summation ai x to the power I, gx to be summation aj x to the power j, okay? And you can compute this inner product now, because you see, this is an inner product defined over the whole V. So this is certainly an inner product over Rx over any subspace as well, right? So what will be your F inner product G? What will be your F inner product G? It will be integration 0 to 1 summation, this should be Bj, sorry, ai x to the power I into, I've written T here, na? Okay, okay, just not a big problem. Bj x to the power j. Let's write it x dx, right? And what is that? Summation 0 to 1 summation ai bj double summation x to the power I plus j dx, right? You take the summation outside ai bj integration 0 to 1 x to the power I plus j dx, right? That is summation ai bj by I plus j. It will be I plus j plus 1, right? Yeah, that's it. Okay. So is that clear? Why this is indeed, why indeed this is an inner product over Rx, right? Right? Now you just take W to be the space of all polynomials of degree less than or equal to n. So, I mean, you were saying that it was not defined. I mean, whether it's an n cross n matrix or not, it was not defined. Okay. So, yeah, there is, I think, a typo. I should have mentioned it that when A is a matrix, I mean, I should have mentioned it that it is a square matrix. Actually, you know what? Is this matrix A positive definite? When we are talking about positive definiteness and all that, we invariably assume that A is a square matrix with finite rank. Okay. Finite dimension. Otherwise, you can't think about X transpose AY. But yeah, I should have mentioned it there. So now you see, you have a basis there, 1 x up to x to the power n, right? Right? You have a basis there. Now you see x to the power I minus 1 inner product x to the power j minus 1. What will it be? What will it be? It will be yes, integration x to the power I plus j minus 2 dx, right? That is 1 by I plus j minus 1. So you realize that inner product which was defined on closed 0, 1, C01, the inner product defined on closed 0, 1, if you restrict it to W, you get the inner product matrix to be this. That is the inner product, the main inner product that is defined on C01. If you restrict it to W, and then you take the inner product matrix with respect to beta, you get back to our A. So it is directly positive definite full rank and everything else. So when I first saw this problem, I only noticed one thing. When I first saw this problem, I only noticed one thing, that it is nothing but 1 by, this term is nothing but integration 0 to 1 x to the power I minus 1 times x to the power j minus 1. That's all I noticed. Because I had the other information. So you see that I already knew that this is an inner product. I already knew that inner product matrix is a positive definite matrix. Okay. So it was just a 30-second solution for me. So now we will conclude the class there, but let me just tell you something. And I think it is extremely important. With his approach, what he was doing, he was, trying to compute it by hand. Okay. There may be a solution. Okay. I haven't tried it by hand because I don't think there is any point of doing that. For a very simple reason. You see, problem solving skills are necessary. But it is, you can solve a problem with 1,000 ways. But there should be two goals of your path. One is to minimize your effort, and the another is to enhance the technicality of the process. That is, to come up with a better process which is good enough to solve more problems. So you see the approach, the approach that he took, I don't know your name yet. I'm not targeting you. Don't think that I'm targeting you, okay? So the problem with when people think this matrix is that they think it, when I'm asking you this problem, when I'm asking you this problem number 4, you are thinking this is a problem of matrices. Okay. You are thinking this is a problem of matrices. So you are thinking in terms of linearity, trace, and all that. When I see this, I am seeing it as a problem of inner product spaces, which is disguised in a matrix form. That's it. And that's the why I give so much importance, even in my academy, to solve textbooks. You see, you solve Hoffman-Kunz, you go through the inner product spaces, and you will recognize that this problem is nothing but a problem from the inner product spaces, which has been, which is taking a disguise in some matrix form. You don't do that, you directly come across the problem and you think that you will be thinking that this is a problem of matrices. And even if I tell you the trick, you won't be able to remember it because you will probably see 1,000 such tricks. Okay. You cannot remember 1% of those tricks unless you are good enough to come up with, with uh, with the trick yourself. If you are not being able to invent the trick yourself, you will never be able to remember it. Mathematics is not about remembering. So that's what I wanted to convey at the very end of this class. That, why was this problem chosen? Why was so many things written there? See, the theory I have developed, I basically developed a theory connecting inner product spaces and positive definite matrices. All is given in Hoffman. So once you go there, you will be able to solve 1,000 such problems, and you will be able to come up with the tricks yourself. But when I tell you that, you are thinking that, see, I could have solved the problem directly. Okay, I could have just solved the problem directly. Okay, I could have solved the problem 4. But the problem would have been that, then you would have thought that this is a problem related with matrices. We are using inner product to solve it. Where it is not true. It is the other way around. It is the problem of inner product spaces, which has been disguised in matrices. That's why I try to choose a problem, a thematic way of a thematic problem, and I try to what should I say, a path which will lead us to solve the problem. And probably you will learn much more than just a trick. Okay. So again, let's conclude the class here. I think sir is here, right? Sir, I will conclude it by saying that.
Thank you, Abhirup.
Yeah.
Any participants, if you want to share a feedback or share some opinion, you can make it now. Otherwise, we will end up here.
So in every class, the class was much more interesting, and the end is very inspiring. Okay, and this comment is more inspiring actually. Believe me, this comment is even more inspiring than the end. Because if you are appreciating this approach, it will give me much more confidence. Because see, there is very much competition in this field right now. To survive as an institute, which encourages solving textbooks, it's almost like what should I say? I'm trying to sell spectacles. I'm trying to sell glasses in a place where everyone is blind. So just Sarah has also encouraged me to do this sort of session. The previous session you can go through. There we have defined a few things. That is also very thematic. Discrete problem solving technique is also very necessary to clear any examination. You have to come up with solutions fast and fast and efficient. But that is the next step. That is the brush up. First, go through the textbooks. Thank you, Yogesh, again. I keep telling it is at the end of every class. We used to solve the textbook, the reference book, then we used to go to the PYQs. We never just did NCRT, the government book, and then we just shifted on to doing IIT JEE level advanced. So that was never the way. And this shouldn't never be the way. Okay. Thank you for tolerating me for this long.
Okay, thank
Thank
you.
you, sir.
Yeah, Dharmendra.
Thank you, sir. I am Tirur from Kasganj, UP, near Aligarh. I am preparing for IIT JAM and ISI and CMI also. Can you advise us some preparation tips for IIT JAM and CMI, which are more advanced, and ISI also, and
See,
books also?
The technique for ISI CMI and the technique for IIT JAM, these are quite different. Okay, because in ISI and CMI, you will have to write down the solutions. Even in TIFR second part, you will have to write down the solutions. The approach we are taking in the class. Okay, that approach we are taking in the class is very much meant for subjective problem solving. But you know what? Suppose this problem can be given an MCQ. As I told you that I have collected this problem from a NET paper. Okay, let me just share the screen again. This was given in NET exam. Okay, so this can be given an MCQ as well, but it will still not take you more than 30 seconds to solve it once you know the theory. So again, my approach is very same. First learn mathematics, then prepare for JAM. That's it. That is it. So first,
yes, sir.
Solve Rudin, Hoffman, Artin, or Hungerford. What that is? Maybe for IIT JAM, you don't need Rudin, but Sherbert will be good enough. So, And then you need those routine, that particular book for, I mean, TIFR and the research institute like IITs and TIFRs and all that. So first go through those books. Then for the last 3 months, before JAM or the last 2 months, just keep solving the PYQs. But that is the last step. That is not the first step. People mistake it by taking the first step. Actually, they start by solving the PYQs, then try to remember the theories. That has never been the way. Okay.
Yes, sir.
Okay. Thank you.
For problem solving technique learning, PG Polya and other book is there and also.
Just solve the textbooks first. Okay. You don't need anything, any other problem solving techniques. Everything is there. Because you see, when an IITian, when a professor from IIT is making the question, he is basically going to Hoffman-Kunz, he is basically going to 𝕨𝕬𝕙𝕚, going to our team. Then he is picking up a question, he is tweaking it, he is adding the options. Okay. So it's better that you go to the source first.
Yes, sir. Yes, sir. Thank you, sir. Thank you very much.
Probably there won't be any more session before IGM math, because I mean that is after 7 days just. But we will definitely come up with more in the next month. Okay.
Sir,
Thank you, Abhirup. Let us wind up here. Sorry for the delay and technical issues from our side. And,
no
wish
issues.
all the participants all success in the coming examinations. With that, let us wind up here. Good night.
Yeah.
Thank you, sir. Thank you so much. Good night, sir.
hello, sir.
Yeah. Go ahead.
I had a doubt that, sir, the exams are just 7 days later. So I have completed my real analysis from schemata and like basic feedback problems and some theory stuff. And so, what should I prepare for more? I mean,
Okay, so my suggestion will be, don't try to prepare for anything else, because see, if you haven't done it, I mean, 7 days will lead you nowhere. Okay, lead you to nowhere. That's not possible. So if you are to crack the exam, you should be good enough to crack it on 4th May. If you want to crack it on 11th, that's all. So don't burden yourself with any more practice. That's all I want to say. Don't burden